Deep beneath the Atlantic waves, 3,000 meters below the surface, the ocean floor stays completely dark and cold. Here lies a thin line of armor and glass, no thicker than a garden hose, carrying light across continents. Suddenly, a heavy commercial fishing net drags along the muddy seabed, snagging the line. With immense force, the steel wire snaps, cutting thousands of signals in an instant. Thousands of miles away, screens flash red in network control centers. Data streams freeze, bank transactions stall, and international calls drop without warning. Millions of people never realize that their digital lives depend on fragile threads sitting on the ocean floor. When one breaks, the hidden mechanics of global communication come to a sudden stop, triggering an urgent emergency response across the sea. Within hours of the break, a specialized cable ship named the CS Reliance receives its launch orders. Docked at a high-tech coastal depot, the massive vessel stores miles of spare fiber optic cable in deep round holds. Engineers load fresh supplies, check heavy mechanical winches, and inspect precise underwater tools. The crew prepares to battle rough swells to repair the invisible pulse of the world network. Navigation officers track precise GPS coordinates pinpointed by light pulses sent from shore terminals. By measuring the exact time it takes for a light wave to reflect off the break, engineers know the fault lies hundreds of miles out at sea. Navigating through heavy wind and high ocean waves, the ship races toward the precise spot where the dark subsea floor holds the damaged fiber cable. Arriving at the target location, the CS Reliance does not drop a traditional anchor. Instead, powerful thrusters along the hull fire automatically, keeping the vessel locked in place despite strong ocean currents. Computer systems monitor satellite signals and water flow to hold the ship steady within inches. On the open sea, this physical stability is crucial before sending heavy gear down to the dark seabed. The crew lowers a heavy remotely operated vehicle, or ROV, over the side of the hull. Attached by a thick umbilical cord supplying high voltage and data links, the robotic crawler sinks into the freezing depths. High-intensity floodlights cut through the pitch-black water, exposing a flat landscape of mud and silt. Cameras stream real-time video back to pilot screens inside the command room on the ship. Inside the dimly lit control room, operators sit in custom leather chairs, clutching joysticks with sweaty palms. The air smells of warm electronics and coffee. Pilots must steer a multi-ton robot through crushing ocean pressures that would instantly destroy human lungs. A single clumsy movement could bury the broken line in thick mud, turning a brief repair mission into days of searching in total darkness. The ROV moves slowly across the ocean floor, searching for the severed ends of the fiber optic cable. Hydraulic mechanical arms extend from the robot frame, holding mechanical pincers and specialized cutting blades. Once the damaged section is located, the robotic arm grips the line tightly. Sharp blades slice cleanly through the protective steel armor, preparing both severed ends to be lifted to the surface. Lifting a broken cable from the bottom of the world is a brutal fight against gravity. The ship drops a thick steel rope into the black water. At the end of this rope is a heavy metal claw. It falls for hours, sinking through the freezing dark until it hits the deep mud. Down in the crushing depths, the remote robot moves in. Its cameras cut through the gloom, guiding that heavy claw right over the broken loop of the cable. The trap snaps shut. The grip is locked. Up on the surface, the mood in the control room shifts to pure dread. The crew holds their breath. They know the terrifying truth of this moment. If they pull too fast, the fragile cable will snap. If it breaks now, it falls back into the abyss, lost forever in the dark. Hours of desperate, nerve-wracking work would be wiped out in a single second. The operators stare at the glowing monitors, their stomachs tied in knots, listening to the heavy deck plates groan under their feet. The ocean does not want to let go. 3,000 meters of water creates a crushing, terrifying weight. The freezing currents pull hard against the ship, acting like a giant invisible hand trying to rip the wire away. The thick mud on the seafloor acts like glue, sucking at the buried line. It is a hostile, alien place, fighting against a thin thread of human survival. The stakes hanging on that single steel rope are massive. This is not just a wire, it is a lifeline. If the winch fails, the screens go blank for millions of people. Entire financial markets freeze. Emergency rooms lose touch with the outside world. The quiet, hidden backbone of modern life is dangling by a literal thread over a bottomless pit. The massive hydraulic winches on the deck finally begin to turn. The heavy metal gears scream as they take the sudden load. Foot by foot, the line is dragged upward. The ship's engines roar, fighting to keep the vessel perfectly still against the crashing waves. It is a slow, agonizing crawl from the dark bottom of the sea to the safety of the sun. High above, on the wet stern deck of the CS Reliance, workers guide the wet cable as it breaches the surface. Sea spray splashes across yellow safety helmets while massive drums reel in the dripping line. The cable is secured in heavy deck clamps to prevent it from slipping back into the dark ocean depths. The initial physical recovery phase is complete, opening the way for micro-precision work. The action shifts immediately from rough deck iron to a sterile, climate-controlled laboratory inside the vessel. Here, highly trained glass technicians replace deckhands. They strip away outer layers of waterproof gel, heavy steel wire, and copper casing. Deep inside lies the heart of the cable, strands of pure glass barely thicker than a human hair, carrying fragile beams of invisible laser light. Technicians carefully clean each individual glass thread with pure alcohol to remove microscopic dirt. They place the glass ends inside an automated fusion splicer. The machine aligns the hair-thin fibers using microscope lenses and high-resolution cameras. A tiny electric arc strikes between two electrodes, melting the glass ends together at over 1,000 degrees. The glass flows into a single seamless continuous thread. Immediately after splicing, engineers run optical tests to measure light loss across the joint. Invisible laser signals flash down the line to shore stations thousands of miles away. If even a tiny flaw or air bubble remains inside the glass junction, the laser signal weakens, forcing technicians to cut the splice and start over. Perfection is mandatory. Once returned to the ocean floor, another failure is unthinkable. Once light flows perfectly, workers rebuild the protective insulation surrounding the glass core. High-pressure injection molds apply heat-shrink plastic, fresh copper cladding, and braided steel wires over the spliced joint. This watertight seal must withstand hundreds of atmospheres of ocean pressure and prevent seawater from touching the delicate electronics. The spliced section becomes as strong and flexible as the original manufactured line. Because the repair adds extra length to the cable, workers form a smooth loop called a bite on the deck. Dropping the cable straight down could create sharp kinks, snapping the fragile glass fibers under high tension. Special deployment wheels gently roll the loop overboard. The ship moves slowly sideways, laying the extra loop neatly on the sea surface as it begins its long descent back down. As the repaired cable reaches the ocean floor, the ROV descends once again into the deep gloom. Equipped with powerful high-pressure water jets, the robot blast cuts a trench into the ocean mud along the cable path. The subsea line settles deep into the soft sediment, shielded from future damage. Within hours, natural ocean currents cover the trench with mud, burying the line under a protective layer. Decades ago, submarine cables were simple copper lines carrying low-grade telegraph signals. Today, over 500 subsea fiber networks cross the globe, carrying more than 99% of all international data traffic. Satellite links simply lack the bandwidth and speed needed for modern society. The entire global internet depends entirely on these mechanical repair ships continuously mending the seafloor network day and night. Without these rapid ocean repairs, global commerce would quickly grind to a halt. Financial markets, cloud servers, and international supply chains rely on constant subsea connectivity. A single unrepaired break can isolate whole island nations or slow down entire continental economies. The quiet work of cable ships keeps the invisible engine of world trade running without interruption, hidden beneath thousands of feet of water. For the crew aboard the CS Reliance, life is an endless cycle of high-stakes pressure and long isolation. Sailors and technicians remain at sea for months at a time, standing guard against unpredictable storms and deep ocean hazards. They work long night shifts under glaring spotlights, knowing that the smooth flow of human communication rests entirely in their mechanical skill and steady hands. With the trench fully covered and final signal tests confirmed, the ROV is winched back onto the ship deck. Engine noise settles to a steady hum as the vessel turns toward its next assignment or coaling station. Down below on the quiet seabed, the repaired fiber optic line pulses with millions of digital thoughts, invisible and untouched by the crushing weight of the sea. Every minute of every day, unexpected subsea events threaten these delicate digital pipelines. Earthquakes trigger underwater landslides, anchor flukes drag across marine corridors, and deep-sea sharks occasionally bite at the outer casing. Yet, within hours of every breakdown, the silent fleet of repair ships moves into action, preserving the fragile links that hold modern civilization together across vast ocean distances. High-tech society often looks to the skies and cloud servers for the future of technology, forgetting the physical world beneath the waves. The global internet is not an airy cloud. It is a physical net of glass and steel laid on muddy seaplanes. As long as humanity relies on instant global connection, specialized maintenance vessels like the CS Reliance will navigate dark waters to keep the world united.